And then next we have Natasha Abrams, who will be telling us about illuminating hidden binary parameter space with Roman microlensing.
Hi everyone, my name is Natasha Abrams. I'm a finishing grad student at UC Berkeley, and I'll be talking about binary microlensing with Roman. So Jessica gave a great introduction on single source, single lens, or point source, point lens microlensing, where you have just one lens passing in front of one source that yields a typical looking like microlensing signal. When we say binary microlensing, what do we mean? So one way is that the source is a binary, that your source star, instead of being a single star, is a bound binary pair, and there's a single lens passing in front of it. And this will yield the superposition of two single sources. You can also have binary lens a binary lens microlensing event, where instead of one lens, you have a binary, and this can lead to very complicated lensing geometries that can lead to very sharp increases in your event magnitude. And so these sorts of systems, if they're well measured, you can constrain things such as the mass ratio and semi-major axis of your binary. So to give an idea, this is an example of a system, the geometry of a binary microlensing system, where in black is your primary lens, in purple is your binary primary lens, purple is your secondary lens, and in blue is your source trajectory. In red here is what's called the caustics. These are areas when the source passes over that you get these really sharp increases in your light curve called caustic crossings. You can see down here the corresponding light curve where when the source passed over the caustic at the beginning and at the end, you get these two really sharp increases. And to give you a sense, when we change the mass ratio so that the secondary lens is half as massive as the primary, the caustics change, and so does your light curve. And here's one more example. And in this case, it's not a caustic crossing. Of course, that's dependent on your source trajectory, but you can get all sorts of different lensing geometries. We can also see what happens when you change the separation of your lenses, where as you increase, you can get, again, different light curves, and if the lenses are far enough apart from each other, they can act as two single lenses. And so what's interesting is that microlensing can probe a unique part of parameter space for binaries. You can get down to really extreme low mass ratios that aren't accessible by a lot of other means. The lowest mass ratio microlensing event found is 10 to the minus 5. Of course, that's for an exoplanet, but especially for microlensing, the math for exoplanets and binaries is identical. You can also probe some more intermediate semi-major axes than some of the other methods. One gotcha, though, is that sometimes these binaries can masquerade as single lenses. So up here, we have a typical point source, point lens microlensing event. And over there, you have an obvious binary with multiple peaks. And down here, we have an ambiguous binary lens. There's some asymmetry. Maybe that's due to what's called microlensing parallax, which can be caused by the Earth going around the sun and viewing the microlensing event from different angles. That can lead to some asymmetry. But in this case, it's a binary lens, and it's very difficult to distinguish those until you do intensive modeling. And so, to get a better understanding of the population and what sort of constraints we can make, the completeness corrections that need to be done, we model them with Popsicle. And so Popsicle, as Jessica mentioned, is a population synthesis code where we start out with Galaxia, which simulates the Milky Way with single stars only. We then inject in compact objects and binary companions using the positions and velocities as informed by Galaxia. You could just take it there and use it to do population synthesis in general. You just got a patch of the Milky Way. But we'll go on, of course, and do a mock microlensing survey and simulate light curves to look at the detectability. So we started out looking at ground-based optical surveys, something like OGLE. And in our simulations, we saw that over half of the microlensing events had some binary, either binary lens, binary source, or both. And this is very different than the approximately 10% of microlensing events that are identified as binary. So we went back and we simulated a set of light curves with OGLE-like cadence and noise from these simulated parameters, and fit them with single source, single lens microlensing events. And we saw that the vast majority of them were fit well by a single source, single lens model. We recovered the approximately 10%. We got about 7% of binaries that are fit poorly to a single source, single lens model. But we're seeing that likely in these ground-based surveys that over half of the microlensing events have some hidden binary, either as the lens or the source. And so what about for Roman? So using the set of simulations that Jessica introduced, we can look at the binary fraction as a function of our magnitude sensitivity. So the way to read this plot is that each curve represents a set of microlensing events. So blue is single source, single lens, orange is single source binary lens, and we are plotting the fraction as a function of the minimum baseline magnitude cut that we make. And we see that as you go to fainter baseline magnitudes, that the binary fraction decreases. And this is specifically for binary sources, and that's because as you're probing towards fainter magnitudes, you're probing towards less massive stars, which have an intrinsically lower binary fraction. And so what this means, though, is that your binary fraction ends up being as a function of where you are in the galaxy. It's a function of your extinction. And so this will be extremely important for when we interpret in the galactic center field versus the lower galactic bulge fields in the microlensing case. Since in the areas of higher extinction, you're effectively probing less faint objects that have a higher, that are more massive stars, that have a higher binary fraction. And this will make an effect. And even though the effect is mostly in binary sources, there can be a lot of degeneracies when you're interpreting whether something is actually a binary source or a binary lens, depending on the source trajectory and a bunch of other factors. So it's important to take into account. While it's difficult to distinguish, though, astrometry may help to distinguish single source, single lens events from binary lens events. So here's a typical light curve and corresponding astrometric signal for a single source, single lens event. Then up here we have a binary lens event where the light curve would be difficult to distinguish from the single source, single lens case, but in the astrometry you have a significantly different signal. And to get a sense, here's a mock Roman event zoomed in on the actual signal, and with the binned astrometry, with typical sorts of error bars that you would fit to get out things like semi-major axis and mass ratio. However, not all your binary microlensing events are going to look like this. And so when you're going from your measured distribution of these quantities to get back out to an actual measured distribution of semi-major axis and mass ratio, you want to take into account the differences between those that are going to be binary microlensing events and have a binary signal, and those that are even microlensed at all. And so we can look at, for example, the semi-major axis distribution for these multi-peaked binary events that are more likely to be identified as binary. And you can see that in blue is our intrinsic binary distribution that we put in before doing any microlensing. In orange are the binary microlensing lenses, and green are the sources. And you can see that these all have different distributions. You can also look at the mass ratio distribution, though those aren't actually significantly differently found. And so I just wanted to highlight some of the recently completed and incoming upgrades to Popsicle, where we have incorporated ruminant Roman filters. Sage Romolia, an undergrad at Berkeley who I've been advising, has incorporated those and enabled this work. We have included binary orbital motion, which can get super wacky, light curves and astrometric signals. Dex Badra, a postbac, who I've also been helping to advise, led this. Macy Houston is adding a more modular, flexible galactic model into Popsicle, SynthPop. And as Jessica mentioned, we are just evolving the stars currently as singles, but we've just completed an upgrade to use Cosmic so that we're able to evolve the binaries, including mass exchange, so you can get a more realistic distribution of black holes, stuff like this. And we also are going to incorporate Cogsworth to evolve objects through a galactic potential, so you can probe things like kicks and how that changes throughout the galaxy, since that'll affect your microlensing distributions. So Roman microlensing is going to be awesome for kind of probing this like interesting part of the parameter space for binaries and in a population and metallicity that hasn't been able to be probed in such detail yet. So I'll leave out my summary and take any questions. Thank you.
Okay, questions?
Hi, that was a wonderful talk, as well as the one before it. I look forward to meeting with you, Jennifer Sobek, Caltech IPAC. One thing I'd like to know, I have a myriad of questions, but one thing I'd like to know is, have you also looked in the F87 and F213 bands?
Yeah, so what's it called? Or I guess maybe we haven't actually looked at the results, but we do have them as part of the runs that we ran, so I'm happy to talk about it in more detail.
And then as a function of source crowding, have you also looked into those effects as well? It's something that we're very deeply concerned with. Okay, then I'd hope to schedule some time with you guys later in this conference. Thank you.
Yeah, for sure. Yeah, we include the neighbor blending as part of the microlensing blending, though I guess source confusion, not as much. Yeah.
I was wondering, it was a great talk. I was wondering about the plot you showed before with the double peaks for the Roman event.
Mm-hmm.
So the Roman event, it basically starts around day 17 and goes to day 18. If that actually didn't start near the beginning of the epoch, but actually started near the end, and you only got one peak of it, are you able to back out from the astrometry or something else what that double peak might look like?
Yeah, it depends. I mean, there's some degree of luck, but the astrometric signal usually lasts longer than the photometric signal. Like as you can see, well, it's actually kind of hard to see in this plot because I cut it off just at one season. But you potentially could, though it would be difficult to constrain it in detail. But I'll say this was one of the random events that I selected from the survey. I didn't purposefully put it in the middle. So there will be things that look like this. There will also for sure be things where the entire event is in the gap, stuff like this, yeah.
All right, I apologize in advance for asking this question, but what about triple systems? Have you thought of this?
Yeah, so I didn't want to get into too much detail because we do cheat a little, but we do have triples. We are not going to have them when we are using Cosmic, but we use the Duchesne and Krauss review paper for the triple fraction, and we just basically draw it as a secondary companion. So they're all basically hierarchical triples. And then where we really cheat is in the microlensing modeling for them, because basically what we do is that we take each pair of the primary and each companion and take whichever one would have the higher delta magnitude and use that as our delta magnitude that we measure. But that's definitely not the correct way to model that. The same way that binaries can introduce a lot more complication into the modeling framework, that you get these costic crossings, you can get additional geometries in triples. And so the idea of that was to just more get the fraction that are triples. And I think that the answer was 3% from our OGO ground-based survey, but I have the table, and I'm happy to talk about it in more detail. Yeah.
There's a request online. Please put up your summary slide.
Sure. Can do. Is there
So, excellent talk. One thing that I found interesting was how the binary fraction changed as you went fainter due to the mass of the primaries. And I'm curious if you can see a similar effect of the multiplicity fraction changing in different galactic populations from the bulge from the disk, et cetera.
Yeah, that would be definitely interesting to look, I guess. So microlensing, basically you probe a slice, right? And so you're not just probing the galactic bulge, you're probing towards the galactic bulge. And so all those populations are kind of mixed up together. And so, in principle, some things can tell you, maybe the color or whatever, but I think, and if you have the photometry and astrometry, Jessica emphasized the mass, but you also get out distances. So, yeah, definitely something interesting to chat more about.
So I think we're going to move to the next part. So let's thank Natasha for the talk.